Okay, so it's 4 p.m. and we're going to resume the session. Uh, on 4 p.m. we're going to have Seonggeun Park from Quick as presenter, who is going to present about complete problems of quantum complexity classes. So let's welcome the speaker.
Okay, hi everyone. I'm Seonggeun Park, and I'll be presenting on the topic complete problems of quantum complexity classes. It's great to see you again. Okay. So here's what we'll be covering this presentation. Introduction to complexity theory, PMP, reduction, BQP QMA, BQP complete, QMA complete. The topic I will present first under theoretical computer science, a field that involves lots of proofs and mathematical formulations. So I won't be discussing the latest research trends. Instead, I'll focus on the fundamental concept of quantum complexity theory. For today's presentation, I'll skip rigorous proofs and detailed equations. I aim to convey the concept qualitatively. You're probably already familiar with the concepts of P and MP because it is a relatively simple and widely known concept. Here, I'd like to provide a more precise definition to lay the groundwork for our discussion. Also, BQP complete can be thought of as the BQP complete can be thought as the hardest problems that the quantum computer can efficiently solve, while QMA complete refers to a class of problems that are strongly believed to be beyond the reach of efficient quantum computation. I'd like to do a quick survey with a few questions. So, if you major in computer science or computer engineering, could you please raise your hands? Okay. Okay, that's perfect. And if you are familiar with the concept class P, MP, and MP complete, please raise your hands one more time. Okay, that's perfect. Then let's get started our main topic. I'd like to share a question with you all. The question motivated me to start studying quantum complexity theory. What is the genuine limit of quantum computers' computational power? These statements below may not be directly related to the field of quantum information science, but I am one of students majoring in electrical engineering who are familiar with classical communication and information theory. In classical communications and information theory, for example, there exists a closed form expression for the theoretical maximum information transfer rate, known as Shannon capacity, like this. So B means bandwidth and SNR means signal to noise ratio. So in the given bandwidth and signal to noise ratio, we can calculate theoretical maximum transfer rate, information transfer rate. So we engineer just need to make system that makes system having information transfer rate as close as to this theoretical maximum information transfer rate. Can you find something similar for the computational power of quantum computers? So can you find the genuine limit of quantum computers' power? So Let's dive into the main topic. In this chapter, we'll define computational models, which are the starting point of computational theory. For someone majoring in computer science or computer engineering, this should be a familiar topic. So let's start with deterministic finite automata. One of the simplest computational machine models. Let's see this together. This Q1, Q2, Q3 is states, are states, and those arrows are transitions. And this bolded arrow means Q1 is the start state, and this coaxial double circle means this Q3 is a step state. So you start here, and the input is final string, and the output is accept or reject. So let's see the example. First, the example one is 01001. Let's go together. 0, 1, 0, 0, 1. We stopped at Q2. Q2 is not a step state because the Q3 is the only accept state. So then this determines the final automata M1 reject this string. And we can try the example 2, 01011 and 01011. And this string arrived to accept state. So this machine accept the 01011 string. And you can see that this means if you get this M1 accepts exactly those strings in A where contains substring 11 because 11, then you arrive the accept state. This means if you get a problem identifying strings that contain the substring 11, then you can provide the DFA M1 to solve the problem. So M1 means an algorithm to solve that problem. And we call like this. This is terminology in theoretical computer science, language and recognize. So we say like this. A is the language of M1, and M1 recognizes A in this case. Although the terms language and problem are technically distinct, I'll be using them interchangeably throughout this presentation. Okay, this is a formal definition of DFA. This finite automata M is a 5-tuple Q sigma delta Q0F. So Q is the finite set of states, and sigma is the finite set of alphabet symbols, and delta is the transition function. So this means this is Cartesian product, and Q is the current state and current input and the next state. So delta means transition function, and Q0 is start state, F is the state of accept states. So in previous example, you can represent this DFA like this. Okay, symbol, alphabet symbol means this 0 and 1. Okay. And let's move on to non-deterministic finite automata. You can think it as DFA with non-determinism. An NFA allows multiple paths and free moves via epsilon transition. If at least one of the possible paths for a given input reaches an accept state, then that input is considered accepted. Let's see the example. AB. So there's a lot of possible paths to first A, and we can choose this A, P, and free epsilon transition to arrive to accept state. So this NFA, this non-deterministic finite automata, accept this string AB. Because this machine accept input if some path leads to accept state, one or more paths. And ABA also be accepted like this, and AA will be rejected because there is no path to arrive to accept state. AA or AA or A, there's no A. So there's no way, no path to arrive to accept state. And AB will be accepted state. Oh. So unlike determinist models where the state transitions are fixed for a given input, multiple paths are possible. Essentially, non-determinism means exploring all possible paths simultaneously. Moreover, if even one of these paths succeeds, the input is considered accept. So non-determinism can be explained from the following three perspectives. Like this: computational perspective, mathematical perspective, and magical perspective. And I love this one, this magical perspective. Now let's see this one. In magical perspective, non-determinism means guessing at each non-deterministic step which way to go. Machine always makes the right guess that leads to accepting if possible. So something magical situation happen, that we can only if possible, we only go to the right guess that leads to accept state. Like when we get ABA, when we get AB, then we don't. There is some situation that leads us to select this way. This is a formal definition of NFA, but I'll skip this. And let's move on to Turing machines. A Turing machine is a more powerful computational model that extends a DFA with additional functionalities. In DFA, we just read our input string one by one from the first. But in Turing machine, there is a head, and this head can read and write. And this head is two-way, left or right. So you can move left or right in every procedure, in every step. And tape is infinite to the right side. So there is infinite tape space. And this Turing machine can accept or reject any time, not only at the end of input. So this is more powerful than automata, deterministic fine automata, because it has a more freedom. And this is former distribution, former definition of Turing machines. And I'll skip this. I want to talk about the church Turing thesis. In computability theory, the church Turing thesis is the thesis about the nature of computable functions. It states that the function on the natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. The thesis is named after American mathematician Alonzo Church and British computer scientist, mathematician Alan Turing. So this means the intuitive algorithm is equal to if there is a natural language to describe algorithm, and there is some Turing machine that corresponds to that algorithm. So if you want to define a Turing machine that can solve some specific problem, you don't have to describe Q, sigma, gamma, Q0, Q accept, like those 7 tuples, but you just write algorithm using natural language in English or in Korean. Then that is what church Turing thesis mean. We have to evaluate the performance of the algorithm or the Turing machine. There are two criteria. One is time and the other is space. So time complexity means the execution time of an algorithm relative to input size. So what is the input size? The input size like this. This input size means this. Input symbols. So time complexity means the execution time of an algorithm relative to input size, and space means the memory usage of an algorithm relative to input size. So there are many complexity classes related to time and related to space. And they have such hierarchy. So you may already know about this, but I will define this precisely. Before defining class P, we have to define time Tn. Time Tn is the set B. Some deterministic one-tape Turing machine M decides B and run in time OTN. So this time Tn means the set of problems that can be solved in time Tn using deterministic Turing machine. And the class P is like this. Union K time n to the K. So the set of problems that can be solved in polynomial time using deterministic Turing machine, using deterministic Turing machine. So the example of class P is pass, the language pass or problem pass. This pass is the set of G as T, and G is the directed graph with a pass from S to T. So if there is S means start point and T is the terminal point, and if there is pass from S to T in graph G, then this GST is the element of the language pass. So this is the proof. You can decide whether you can decide some element is in pass or not using this algorithm. So on input GST, mark as mark starting point like this, start point like this, and repeat until nothing new is marked. And repeat those things, nothing new is marked. For each marked node X, scan G to mark all Y where X, Y is an edge. So this is an X, marked X. So we have to mark this one and this one like this, and repeat like this, and accept if T is marked, reject if not. So if there is some pass, then finally this T, no T will be marked like this. And you can calculate the time complexity of this algorithm. The first iteration statement is less than n iterations because there are this n means the number of vertex, number of nodes. So there is less. So there's n nodes, so you don't need to iterate this more than n iterations, and so on. So the total time complexity of this this algorithm is O n to the 4 by multiplication. And I want to define the class MP, and we have to define three things. This on NTM runs in time Tn and n time and MP. So on NTM, non-deterministic tree machine runs in time Tn if all branches halt with in Tn steps on all inputs of length n. And n time Tn means some set of problems. Some one tape non-deterministic tree machine decides B and runs in time of Tn. And NP means the union of n time and the k. So this means non-deterministic polynomial time decidable languages. And it also means easily verifiable problems because you can see this picture. There are many branches you can go, and non-deterministic tree machine go all of these paths simultaneously. And the longest path, the time to go to this longest path is Tn. Then we can call this algorithm is in n time Tn. And if some magician give us some hint, if you select this path, and you can arrive a step. Then if we get such if we get hint like that, then we can use hint and verify that they will lead to a step state. So the example of MP is Hamiltonian path, this, which is the set of GST, and G is the directed graph with a path from S to T that goes through every node of. So this is in MP. So I will skip this. So this is just a proof. There is a Hamiltonian path means a directed or undirected graph with a path from S to T that visits each vertex exactly once, and there is graph and start point and terminal point. There is typo T. We can select the path like this, like this. So this is accepted input, and there is various paths to go to search the path, the Hamilton, to find the Hamiltonian path to from S to V. But if there is a magician Bolin who gave us hint, right? Try C first, then A, B, D, and E. So C, A, B, D, E. Verification is easy, but in this case, we can't draw Hamiltonian path because we start like this and we can't go this node again. So there is no path to make Hamiltonian path. Then Bolin also can't give us a hint. This is class MP, and I want to talk about the reduction. A reduction is a way of converting one problem to another problem in such a way that a solution to the second problem can be used to solve the first problem. So you can see the problem A, finding your way around the city, and problem B, obtaining a map of city. So if you obtain a map of city, you can find your way around the city. So if you solve the problem B, then you can solve problem A easily. So if A reduces to B, we can use a solution to B to solve A. So if A is reducible to B, then solving B gives a solution to A. This means if B is easy, then A is easy. Easy to solve. Then it also means if A is difficult, then B is difficult. Then we will find the hardest problem that quantum computer can solve efficiently by using this reduction. And there are many types of reduction. Okay. There is a concept mapping reducibility. A is mapping reducible to B if there is a commuter function f where W in A if and only if FW in B. So like this. And if this reduction function can be computable in polynomial time, we call this reduction as polynomial time reduction. So A is polynomial time reducible to B if A is mapping reducible to B by a reduction function f that is computable in polynomial time. So you can convert this problem to this problem in polynomial time. Then it means if B is in P, then A is in P. Because if B is in P, we want to solve this problem A, then we can convert this problem to B in polynomial time, then solve this problem B in polynomial time because B is in P. Then we solve the problem A. So this theorem, we can prove this theorem. And there is Kuhn-Levin theorem. That means, move on to next slide. Kuhn-Levin theorem means this. I will talk about this later. And this is the example of polynomial time reducibility, but I will skip this because this is just an example. And there is a time limit. So I want to talk about NP complete. So B is NP complete if B is in NP and for all A in NP, A can be polynomial reducible to B. So if B is NP complete, then and B if B in P, then P is equal to NP. That is the meaning of NP complete. So many people don't believe this is true. And so the real Kuhn-Levin theorem statement is satisfiability is NP complete. So many people believe that P is not equal to NP, and NP complete can be considered as the hardest problem to solve among NP problems. So if this NP problem, if someone proved this NP complete problem can be solved in polynomial time, then he proved P is equal NP, and that is many people don't believe that P is equal to NP. So qualitatively speaking, B being NP complete means that B is one of the hardest problems in the class NP. And let's move on to the real main topic, BQP and QMA. Okay, we just talk about P and NP. And there is another complexity class, BPP, MA, BQP, QMA. And there is relation with these six complexity classes. The first law is this P and MP is using deterministic Turing machine, and MP use non-deterministic Turing machine. And qualitatively speaking, the class P means the set of problem which can be solved efficiently, and MP means the set of problems which can be verified efficiently with a proof with some hint by modeling. And you can add you can add randomness and bounded error. Then P becomes BPP and MP becomes MA. And if you add quantumness to BQP, then BQP becomes BPP becomes BQP, and MA becomes QMA. So this is just a qualitatively speaking statements. So BPP is efficiently solvable with randomness, and MA is the set of problems which is efficiently verifiable with randomness and a proof. BQP, efficiently solvable with a quantum computer, and QMA, efficiently verifiable with a quantum computer and a quantum proof. So this is the definition of BPP. If you are majoring in computer science, you are familiar with the definition of BPP using a probabilistic Turing machine, but we can extract the randomness from the machine, and the extracted randomness is in here. We extract the randomness from that machine. So the definition of the BPP is this: a language L is in BPP if there exists a deterministic Turing machine M and fixed polynomials S and R, such that for any input X, M takes in string Y, holds in at most of R and time steps, and so if X is in L, then for L listed 2/3 of the choices of Y, M offset. And if X is not in L, then for at most 1/3 of the choices of Y, M offset. So it allows the error rate at most 1/3. Okay. And this Y is the randomness because it tells us it means the random choice. But BPP is semantic classes, so we need to define promise BPP. This is an important thing in theoretical computer science, but I will skip the detailed description. And I will just define promise BPP. Promise BPP is very similar to BPP, but we just add a invalid. So this promise problem means that a promise problem is a partition of strings into 3 sets: a yes, a no, and a invalid. So if these if some machine get languages that in a invalid, then they that is an invalid input. So the machine can output the machine may accept or reject arbitrarily. So the other case, a yes and a no, this is the same with the BPP. So we finish the BPP. We add the randomness and allow the some bounded error. And before we define BQP, we have to define the P uniform quantum circuit. So why do we have to define circuits? All the quantum Turing machines are well defined. It turns out that quantumly, the most natural computational model to work with is the circuit model, applying gates like Pauli matrices to wires. Unlike a Turing machine, however, which can take strings X of arbitrarily sized as input, a circuit size is fixed. So Turing machine has an infinitely long tape, so it can take strings of arbitrary size as input, but circuit is the size of the circuit is fixed. So we have to use a circuit model to define complexity classes. So given an input X, we require an efficient algorithm for generating a description of a circuit C, which takes inputs of the right size X, absolute value of X. So then P uniform quantum circuit family means a family of quantum circuits, Qn, is called P uniform if there exists a polynomial time Turing machine M, which given as input unary with length n outputs a classical description of Qn. So there is an example. This is not not quantum circuits, but I think this is good example to understand what is the P uniform circuit. This is parity check circuit. Turing machine. This is circuit, so the size is fixed. This circuit can get 2 input lengths. This circuit can get 3 input lengths. This circuit can get 4 input lengths. And these all things do parity check. This is gate called XOR. Then it means the input size, the number of input size is proportional to the number of gate, like this. 2 input size and 1 gate. 3 input size, 2 gate. 4 input size, 3 gate. So the number of gate is proportional is polynomial in the number of inputs. So this circuit, this parity check circuit, is a P uniform circuit. And you can exchange this classical gates to quantum circuit. Then that is P uniform quantum circuit family. So BQP. We define BQP, and there is a nasty statement here, but we'll just see this picture. A promise problem A is in BQP if there exists a P uniform quantum circuit family Qn and polynomial Q satisfying the following properties. For any input X, Qn takes in n plus Qn qubits as input, consisting the input X in register A. This is input, and Qn answer qubits initialized to 0 in register B. So this is answer. The first qubit of B, denoted B1, is the designated output qubit, a measurement of which in the standard basis after applying Qn is the following those things. If completeness, if X is in yes, then Qn offsets with probability at least 2/3. If X is in no case, then Qn offsets with probability at most 1/3. And in valid case, this machine can accept or reject arbitrarily. So this is input, and we want to solve this problem. We want to decide this input is accepted input or rejected input by measuring the first qubit of ancilla qubit. And the size of Qn is polynomial in the input size. Is the number of qubit size. This is BQP. And we have to talk about MA. MA means there's input and some classical proof and some randomness bit. So you get input and Modeling gives us some classical proof, some hint. Then you can solve this. You can solve this problem in polynomial time using randomness within some error probability. And here the error probability is 1/3. Okay. And QMA. QMA is this. A promise problem is in QMA if there exists a p-uniform quantum circuit family and polynomial PQ satisfying the following properties. So for any input x, Qn takes n plus Pn plus Qn qubits as input, consisting of the input x in register A. So Pn qubits initialize to a quantum proof. So in this case, we can get Modeling give us quantum proof. And Q ancilla qubits initialized to 0 in register C. So the first qubit of register C, denoted C1, is the designated output qubit, a measurement of which in the standard basis after applying Qn is the following. So the following those things. So this means if the problem is in QMA, we can solve this problem using quantum circuit, using quantum circuit and quantum proof. Then we can design this quantum circuit in polynomial time. So this is the total diagram. And okay. And B is, I want to talk about the BQP complete and QMA complete. BQP complete is the some languages. In here, B is BQP complete if B is in BQP, and for all A in BQP, A can be reducible, polynomially reducible to B. So we can tell that the problem in BQP complete is the hardest problem that quantum computer can solve. So qualitatively speaking, B being BQP complete means that B is one of the hardest problems in the class BQP. So B is one of the hardest problems that quantum computer can solve efficiently. So this is the example of a BQP complete problem. The name of this problem is MI, matrix inversion problem, which is related to HHL. So you can regard HHL algorithm as the hardest is the algorithm that solves the hardest problem that can among quantum computer can solve efficiently. So I will skip this detailed statement. So you can prove the containment of MI in BQP using HHR algorithm, and you can prove BQP hardness using some lots of equations. Then I'll skip those things. And QMA complete. B is QMA complete if B is in QMA, and for all A in QMA, A can be polynomially reducible to B. So qualitatively speaking, B being QMA complete means that B is one of the hardest problems in the class QMA. So just as MP complete problems are believed to be intractable for classical computers, QMA complete problems are believed to be intractable even for quantum computers. So this is the example of QMA complete problem. The example is in next slide. So we have before 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 the before the example of QMA complete problem, we have to see the definition of K-local Hamiltonian. What is K-local Hamiltonian? Harmonic operator H acting on n qubits is a K-local Hamiltonian if it can be written like this. So it means that we can see the example. This is two local Hamiltonian, and in this case, this one is effectively has effect on two qubits, and two qubits. So this H2 is also two local Hamiltonian. So there is some equation. So if the Hamiltonian is can be represented as the sum of Hamiltonian, which affect at most k qubits. Then the example of QMA complete problem is K-local Hamiltonian problem. So what is K-local Hamiltonian problem? Fix a polynomial P. The promised problem K-local Hamiltonian is the local Hamiltonian problem is defined as follows. So the input is this, a K-local Hamiltonian H, and efficiently computable threshold holds functions alpha n, beta n. And the output is this. So this means K-local Hamiltonian problem can be regarded as finding minimum eigenvalue of given K-local Hamiltonian. But for K is bigger than 2, K-local Hamiltonian problem is QMA complete. So this means even K2 local Hamiltonian is such simple Hamiltonian, but it is hard to find a ground state energy level, even if using we use quantum computer. So this is some disappointing issues, but many researchers or physicists, computer scientists talks like in real situation, in real physics system, there is some symmetry and some restrictions. So in that case, we might use quantum computer to solve that system, that Hamiltonian system, within polynomial time. So this is the oldest thing that I prepare. So thank you for listening. And if you have any question, please feel free to ask me. Thank you.
Okay, so if you have any questions, please feel free to ask.
Yeah, there are many problems. So uh, in the Google Drive, I don't write the reference here, but there is some reference paper about that BQP complete problems. Yeah. Um, uh, 그러니까 P랑 NP를 사용할 때 그래프를 이용해 설명을 했는데 그게 좀 더 다른 문제를 적용할 때 도움이 되냐고 물어보셨는데 어, 여쭤보셨는데 저는 약간 좀 여기서는 좀 정성적인 이해를 도우려고 그 좀 더 이제 한눈 이 글자들이 너무 많다 보니까 그 그거를 이제 좀 이렇게 좀 중화시키려고 그런 걸 도입했고요. 그래서 좀 이해하기 쉽지 않을까, 좀 더 이제 덜 지루하지 않을까 해서 좀 넣은 목적이고, 어차피 그 결론은 어차피 똑같은 말이어서, 딱히 뭐 직관에 도움을 준다거나 그런 거는 없을 것 같긴 합니다. 네, 네, 감사합니다. So is there any more question? Okay, thank you.
Okay, thank you very much. Now it's like 4:50. We're going to have a 10-minute break and start at 5 p.m. Thank you very much.